All right, the banked corner question. Okay, so uniform circular motion, driving on a banked corner. So you want to visualize this kind of thing. To help you visualize it further, I've got a couple videos ready to go here that, figure out where they are. Here we go. Here we go. It's in the other browser. So this ball is going to be just going back and forth, round and round in uniform circular motion on this banked corner, right? It's like a ramp that goes in a cone shape. So very clearly has nice uniform circular motion. That's the type of thing we're analyzing here, and you might have seen something like this in one of these little wishing well things in a mall or a store somewhere, right? The coins go around and around with approximately uniform circular motion. Obviously, the motion slows down and they fall down in fairly quickly, but they go around and around, right? So a car on a horizontal, in horizontal uniform circular motion on this like slippery track. So picture a freezing rain day or something where it's just glare ice, but if you had the right speed, you would just be able to slide through that corner, right? So we want to analyze this. You want to look at the force analysis of this. Great first step would, of course, be to think about the free body diagram, right? So I've got this ready to go where we've got a force of gravity on the car and then a normal force from the surface of the ramp, right? And that's where we're going to analyze a lot about that, right? So the component of the normal force in the direction towards the center of the circle, that's the only force that's providing the force towards the center that we need for centripetal acceleration and to be traveling with uniform circular motion, right? So we know that the x component of the normal force is your centripetal force. So that's right here, like that. Okay. So just to relate back to the non-inertial reference frame stuff, in the car, you're in a non-inertial reference frame, and it would feel like you're getting pulled outward, but really what you're feeling is the force of the seatbelt, the chair and the seatbelt and everything around you pushing towards that center, right? So that fictitious force of trying to throw you outwards has a very real effect in that non-inertial reference frame. But in reality, of course, in the Earth reference frame, you know that you're just traveling in a circle. All right, so those are done. And so hopefully it's obvious at this point, if there's a specific speed that is needed for uniform circular motion. If you're going too fast, you'd spiral outward to a larger path. If you're going too slow, you'd slide into a smaller diameter path, right? So that's what we're going to want to try and analyze and think about here. Now there's a trick with these that I sometimes fall into as well. So I'm going to try and make sure to emphasize it here. The trick to analyzing this is that to recognize that you're definitely we're defining this as horizontal uniform circular motion, which means your up and down is not changing, right? So the car is in a horizontal circle motion, right? Traveling in a horizontal circle. So first of all, like one of the things we could say is while you're traveling in circular motion, then you must have a net force equal to a centripetal force, right? So in this picture of there's the ramp, right? And there's that horizontal circle we're in. We know there must be a centripetal force for that centripetal acceleration. So we're going to choose the direction system where your x direction's in the direction of acceleration. Pretty typical for us to do. So vertically, this thing's not moving up and down, as I said a second ago. And so, acceleration vertically, true up and down vertical, is zero. So the net force in the y direction is zero. So that means that all the forces in the y direction have to add, the up and down vertical direction have to add to zero. So you've got a gravity force and you've got some other force, right? Well, you've got the gravity force, and then we have some kind of force that's balancing that. Okay, and so the question is, okay, well, what force is that? What's balancing it? Well, it turns out that it is one thing first before we get to that. But I just want to point out that in the past, you would have situations where you're on a horizontal surface. And it's definitely, logical to say vertically here, we've got things balancing to zero. Seems really similar to this, right? Vertically balancing to zero. Things are a little bit different, though, when you look at it carefully here. So in this situation, what I would say, this is just a normal analysis, right? The net force is zero, and so it turns out the normal force has to be equal to the negative of the gravity force, as usual. you might think of this and think of it as like the car or the object's not rising up off of the ground, and so the acceleration in that y direction perpendicular to the road is 0. In the circular motion case, all right, this is not true. Okay, the acceleration, the net force perpendicular to the ramp, like that, and the acceleration in that direction is actually not 0, which is strange, right? Because the car is not lifting up off the ramp, but it's just because we're accelerating. You're going to see soon once we finish the analysis, because we have an acceleration towards the center that it equates to. There's actually some acceleration vertically as well, because there's a component in that direction. Right, so if you look at this direction, like this force here, would be a force perpendicular to that ramp as a component. So when we are analyzing this, we're going to look at the normal force. Okay, so there's going to be a normal force off of the ramp, just like we saw earlier here. Okay, so this is where we'll analyze it and get used to how this works. So the centripetal force comes from the x component of the normal force, and the force that balances the gravity force that we were talking about earlier is the y component of the normal force, right? So there's that y component of that normal force. So what happens is typically you would know, say, the force, right? The blue force here, the normal force. You'd typically know it and then componentize it. Whereas in this case, we actually know this value. We know this value has to be equal to the opposite of the gravity, right? And that is the component, right? So it's almost like you're uncomponentizing, if that's a word, and I'll show you what I mean by that. Okay, so here the value of the component is known, right? Fny is equal to the opposite of gravity. So you're going to use it to determine what the value of the normal force would have to be in order for that component to be equal to gravity, only up, right? So yeah, we know the normal force y component of it is mg, and we know that the normal force y component equals the normal force times cos theta. So really, you're just solving out. You have your mg that you know that thing is, and so you divide out cos theta from both sides, and you get the normal force is mg over cos theta. Okay. One thing to note here with this, maybe I'll say that in a second. I'm going to point out eventually here that this force here is bigger than the gravity force, right? And that's not a normal. That's not usual. Let's say. So I don't use the word normal too many times in a minute here, but typically that's not the case, right? Typically you're going to have the normal force matching. In this case, the normal force is bigger, and that happens because of the mechanics of this uniform circular motion situation that we're in. So for that uniform circular motion idea, we know that the x component of the normal force, right, is, so that in this case, the x component, you can see opposite that to get that horizontal would be sine, right? So Fn sine theta, like normal for our componentizing stuff. And so then the normal force goes in as your m 9.8, or mass times g, mg really, over cos theta. And then when you analyze that, you say, okay, well, that's equal to the centripetal force, which is v squared over mv squared over r, sorry. So a nice thing happens here where we notice that mass doesn't matter. So when engineers are designing a roadway, they don't need to worry about the mass of the vehicle. They don't have to design the angle for a particular average weight or mass of a car. The masses don't matter because all objects accelerate due to gravity at the same rate, right? So it makes sense. So mass doesn't matter. And then the other thing we need to do or can do here is we can notice that sine theta over cos theta is the same as tan theta. And that little trig identity is going to help us see there in a sec. Right? So really we're getting v squared over r equals g times tan theta, or 9.8 times tan theta. On Earth, it's 9.8. So in this equation here, obviously, if we had any two values, we could determine the third, right? And so especially, thanks to that trig identity, it's easy to solve for theta. You just do tan inverse, right? It'd be a little tricky, of course, if we didn't have the trig identity. So you hopefully have seen trig identities and trigonometric identities in math class. Here's a case where, the physics of the situation requires that level of math ability. So you can actually solve for the angle. And that's the first question in your homework is actually question number 5, but it's the first one in the list. Okay, it's page 133, number 5. But I keep those numbers, of course, so you can cross-reference to the textbook easily, right? But I try to organize them in a nice order for you to do. Obviously, this equation could solve out for v, or you could solve it out for r, or you could solve it out for theta. It's common to see this one, right? Please note, um, this result, of course, can be used for results in uniform circular motion in a frictionless banked corner. But physicists have to be able to work through the logic that leads to that result. Like that result's created by a person with physics knowledge. That's what you are learning right now, right? You're learning how to do this. So that's required for us. An engineer, if they're just doing a bunch of calculations over and over again as part of their job, or someone who's like a mechanical or a civil engineer, sorry, for a township or a city or something, they're going to have to calculate what angle to make the road at. And so they could just use the equation, of course, because they're not doing new physics. They're just calculating results that a physicist determined, right? They're using physics results that physicists make do for them, and then they just run the numbers. So higher level physics analysis and ability is needed to tackle new situations, of course, right? That's why this is required for you. You can't take question number 5, the first one in the homework, and just take this equation and calculate an answer. Obviously you physically you can get an answer, but that doesn't count for like a full set of knowledge and ability for the course. Okay, because this is a physics course. You need to be able to figure stuff out, not just use a result that someone else figured out, right? That's what engineers do. Engineers just use results that someone else figured out. Sorry, engineers, but that's kind of how it is. Anyways, so I'm sure some of you are looking at becoming an engineer. That's literally what you'll need to do. You'll need to be able to use equations. But for the physics part of it, if you want to be able to get to know how to do something new, that sort of physics knowledge comes in, right? Anyways, here's an example. You're given the mass of the car. You know in advance you don't even need that. Radius is 80 meters. That's the roadway, right? The way the question's worded when you read it, and it's banked at an angle of 20 degrees. Question is just what velocity is needed for uniform circular motion, so that you don't need friction to stay on at that portion of the ramp, right? So so as I did in the lesson here, the main thing is vertically acceleration in the y direction is 0 because we're staying in that horizontal circle. So we'd have net force in the y direction 0, as I looked at earlier, right? So that's basically showing that this force here, the normal force y component, has to be the same as the gravity force. And so there it is. It's actually just calculated as a number here instead of just mg. And then that value allows you to figure out the value of the normal force. And that's this purple here, right? So this green value here of 9,800 allows us to figure out the normal force, which is, again, backwards to how you'd normally do components, right? But the normal force y component is equal to the normal force times cos of 20. And so you just divide both sides by cos 20, and you end up with this larger force, right? This is what I said I was going to mention later in a slide, that normal force is bigger than the gravity force. And that's only because you're in that circular motion, right? You're hitting against that wall, against that sloped road, and using it to help push you towards the center, right? In general, this thing is mg over cos theta, right? As we saw. And so then the horizontal acceleration portion of it, your normal force in the x direction, is your centripetal force. So if you calculated this value as a force, then you need the mass, the actual force values. You need masses. So for how tough the roadway needs to be, how much type of large rocks you need below the surface to provide the support. If a roadway is not rated for a transport truck, that's why the forces are going to be too big. It's not that the speeds would be a problem. So yeah, over here you'd have this. It just, because this mass was given when I did these calculations, I just used them. But we definitely would have ended up with this same kind of situation here where the masses would have canceled out. And you can visualize that right basically here, right? Because this force has a mass, this thing has a mass in it, and this thing has a mass in it. They technically would cancel out. And they even do cancel out actually right here when I divide both sides by 1,000. Like they're gone, right? So anyways, so then you have the acceleration. Once you have the acceleration, this goes into v squared over r, solve for the velocity. Okay, could have used this result, but I mean, again, it's that's only if you're just trying to get an answer for a situation you already fully understand, right? Numerical answers versus physics understanding. Okay, so that is that. So there we go. As usual, thanks for watching, and see you later.